Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. It's an honor and pleasure to present my work entitled Numerical Investigation of the Performance Analysis of a Rigid Rotor Supported by a Hydrostatic Journal Bearing Lubricated by Magnetic Fluid. My presentation begins with problematic objective of study ferrofluid hydrostatic journal bearing, ends with conclusion. In rotating machinery, more performance enhancement is in demand in terms of speed and accuracy. However, these machines face two vibration problems caused by mass imbalance, bearing defect, especially in high-speed rotating machinery. For subject of vibration stress, there are three kinds of control: passive, active, and semi-active. Smart hydrostatic squeeze field damper using and ferrofluid as a smart material is effective in reducing to rotor vibration when the rotor passes through the critical speed. This work describes a theoretical study concerning the performance characteristic of a smart hydrostatic journal bearing using a ferrofluid as smart material. A linear modeling was performed in order to study the performance characteristic of a capillary compensated four-part hydrostatic journal bearing in order to investigate the effect of ferrofluid and static eccentricity ratio on carrying load capacity, flow, and the dynamic characteristic stiffness and damping of hydrostatic journal bearing lubricated with ferrofluid. Ferrofluid or magnetic fluid is colloidal dispersion of magnetic nanoparticles is a carried liquid. The diameter of nanoparticles is between 5 and 20 nanometers. Ferrofluid responds immediately to the applied magnetic field. In a uniform field, the particles align with the field. While is no uniform field, the fluid responds as homogeneous magnetic liquid, which moves the region of the highest field. These fluids can be precisely positioned and controlled by an external magnetic field. Because of this unique advantage, ferrofluids have several applications like computers, dampers, heat transfer, bearing lubrication, biomedical. Since the innovation of the ferrofluid in 1979 by Winslow, attention has been paid in order to increase the theoretical properties induced by magnetic field. This effect is termed the magnetic effect. It is well known that the ferrofluid's viscosity can be controlled by the magnetic field and by the concentration of magnetic particles. That's why it's important to investigate the influence of particle concentration on ferrofluid lubrication. In this study, the hydrostatic journal bearing is composed of four identical plane hydrostatic bearing pads. Each pad feeds with a ferrofluid by recess, which is supplied by an external pressure through a capillary structure type hydraulic resistance. The choice of hydrostatic bearing is based on static characteristics, which are carrying load capacity, flow rate requirement, and dynamic characteristics, which are stiffness coefficient and damping coefficient. The calculation of hydrostatic journal bearing characteristics is done by considering the hydrostatic journal bearing as the juxtaposition of four hydrostatic bearing flat pads. the equation for carrying load capacity and flow requirement. In the linear analysis, the fluid film of the hydrostatic journal bearing can be modeled by a coefficient, 4 stiffness coefficient and 4 damping coefficient. The Reynolds equation allows the computation of the distribution pressure. It must be noted that for a high respect ratio, the flow is neglected along the x-axis, which means that there is no variation in the pressure. The recessed pressure for each hydrostatic bearing pad is obtained by resolving the flow continuity equation. At the point of operation, when the hydrostatic squeeze film damper is in the central position, the following relation are obtained with the bearing characteristic is as flow, are set as a flow. The figure shows the relationship between the lubricant film thickness and the pressure ratio. When the magnetic field is 0 with speed. For static characteristic analysis, we have load capacity values, eccentricity ratio for different magnetic field, and the flow rate varies the eccentricity ratio for different magnetic field. The stiffness coefficient varies the eccentricity ratio for different magnetic field. That's for dynamic characteristic analysis, and damping coefficient varies the eccentricity ratio for different magnetic field. A linear modeling was performed using analytical method in order to investigate the effect of magnetic field on carrying load capacity, flow, and the dynamic characteristic of 4-pad hydrostatic squeeze film damper using capillary constrictor type hydraulic resistance. The result can be summarized as flow. The magnetic field has no effect on the flow rate. When an unmagnetic field is applied, the viscosity of ferrofluid increases, and this leads to a decrease in the load capacity. The damping coefficient is not influenced with the application of the magnetic field. The stiffness coefficient decreases when applying a magnetic field. Thank you for your attention.